Okay, this is going to be a video about sums, and more specifically, the sum of consecutive powers of integers. And I've written three equations right here that you should find quite interesting if you have any sense of observation. These are powers of 3, and here there's a 2. These are powers of 4, and here there's a 3. These are powers of 5, and here there's a 4. And here there's a minus 1, here there's a minus 1, here there's a minus 1, here there's the next power of 3, here there's the next power of 4, and here there's the next power of 5. So if we generalize, um, I can prove this, of course. This isn't just gonna be me writing this equation and saying like, hey, this is true. Wait, actually, I can do this. Oops, to the n, a to the I shouldn't have done that. Whatever. A to the n plus 1 minus 1 divided by a minus 1. Oops, a minus 1. There we go. Didn't make any mistakes there. That's quite interesting, isn't it? So this, if you wanted to write it in words or using the sum symbol, which I cannot use on Notepad, or maybe I can, but I don't have it anywhere where I can copy it and paste it. So it's simpler to just say the sum of in words, or type that in words rather. So what exactly was I saying? I'm not sure. So let's just move on. So if you want to prove this, you could say, okay, is this true? We're gonna go by what is it again? A proof by induction. There we go. It means that if it's true for n, it's true for n plus 1, and then you just have to find one n where it is true, and you know that every n equal or bigger to that one is true. So we have an example where it is true. For n equals 3 or 4 or 5, it is true. Or at least for a, what am I saying? And I'll prove that it's true for... Can I prove it's true for any a? I think so. Let's just do this. Okay, so how exactly did I do this again? This is not really optimal. I didn't prepare at all. So let's just try this. Basically, if you do the sum from 0 to n, this would be, a to the 0 to a equals n. But let's say to n plus 1 minus sum from 0 to n. So basically, imagine instead of you have a to the 0 plus a to the 1 plus a to the blah 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 all the way up to a to the n plus 1, and then you remove this exact sum, but you don't go up to n plus 1, you stop at n. The only thing you're left is a to the n plus 1. And if you take this term I wrote over here, and instead of going, you add 1, so you go from, instead of having n, you put n plus 1. So this n is going to be n plus 1, and this one is going to be n plus 2. So you have n plus 2 minus this equals a to the n plus 1. And we can actually see that very easily by seeing that it's going to be basically this. We can write them on a common denominator. Let me just try to do this. Let's remove this divided by a to the minus 1. Let's remove that. Let's remove these two minus 1s because they cancel out. Is this 2, 2? I think I have a parenthesis that shouldn't be there, something like this. Okay. 1, 1, 1, yes. And what was I doing exactly? That's gonna be... Okay, so this might not say anything to you, but I'm going to try to make you visualize it. Imagine a is an integer, for example, 11, right? That would mean that this is 11 to the, let's say it's 20, right? 11 to the 20 minus 11 to the 19. What is this saying, you know? The only thing this is saying is that this is 11 times bigger than this, really, because this is 11 to the 20 minus 11 to the 19. So what we're basically saying is that one is a times bigger than the other, right? And what it really is a minus 1 times a to the n, n plus 1. And if you factorize that and divide it by a minus 1, if you factorize that, I mean, this is a factorization. What am I saying? If you do the distribution, you do a times this minus 1 times this, and you'd get exactly this. So all I've done is factorize it, put it in two terms, and now this a minus 1 cancels out with this a minus 1, and what you're left with is a to the n plus 1, which is exactly this. So now you might be saying, okay, what the hell, where did this lead us? Well, what I've done is I've taken this sum right here, and I said, if instead of going all the way up to n, you go one further, the difference between that sum and the sum you were at when you stopped at n, so instead of stopping at n, you go to n plus 1, and then you remove the sum where you stopped at n. The difference between those two sums is a to the n plus 1. And that's quite easy to see because it's sums. So it's just the last term that you changed, that you added rather. And for this side, this is this part. And I've said, okay, this is going to be true if this difference between n plus 1 and n plus 2 is the same as when this side between n and n plus 1. And it is. I've just proven that the difference between these two things is actually a to the n plus 1. So this a to the n plus 1 minus 1 divided by a minus 1 is equal to this sum, because every time you increase the n, it stays true, and whatever the a is, it stays true. So this is always true for every n bigger than 1n. Well, bigger or equal to an n, you can prove it is equal to. And I've just proven it for like this one. You can try it yourself if you want to. Otherwise, I can just do it myself. That's going to be 4 plus 36 plus 108 equals 728 divided by 2. That first sum is 48. 148? Nope. Oh, I forgot to add the 243. That would make sense. 243. Okay, so that would be 40, 148, 348 plus 43. And this sum this thing 728 divided by 2, that's 350, 364. And this isn't 364. What have I done? Oh, it's because this is 348, isn't it? Oui? Okay. Wait, 348 plus 43? Where have I messed up? I am so bad at doing shit like this. How can I be so terrible? I've put the 27 twice. What a dumbass. Oh my god. I've put the 27 twice, actually. What am I doing? Let's try that again. 121. That's actually really cool. What? Have I messed up then? Surely I have. This is not 121. It is. Wow, that's amazing. Wow. I just need the meme face guy to do this, but I'm not gonna put that in the video. But you see, interesting patterns pop up everywhere. Okay, plus 243, and I just made the weirdest hand movement ever. But that was cool. And then this is actually equal to, well, these two are equal. It's quite easy to see that this is 364. So yes, these two lines are actually equal. So we know that for every n bigger than, well, I guess it's quite easy to see why it's equal for a to the 0. So guess I didn't really have to do that, but it's always fun. Except I fail at putting calculations correctly for like more than 2 lines. I always make a mistake, but that's fine. What exactly am I doing right now? Yes, and we can know that the sum from 1 to infinity of 1 over I, yeah, from I equals 1 to infinity of 1 over, 1 over a, oh my god, 1 over a to the I is equal to 1 over a minus 1. And this is basically, imagine summing up every power of 2 in the negative way, so like 1/2 plus 1/4 plus 1/8 plus a 16th plus a 32nd. I don't know. Certainly not a 32th, so whatever, you just sum up all the inverse powers of 2, and when you sum them all up you get 1, because it would be 1 over 2 minus 1, which is 1 over 1. And if you sum up all of the powers of 3 in the inverse way, so 3 to the minus 1 plus 3 to the minus 2 all the way up to infinity, you'd get 1 over 3 minus 1, which is 1 over 2. And that's actually one of my coolest equations. Summing up all thirds gives a half. It's actually really cool. Summing up all halves giving a whole is actually not impressive, but all thirds giving a half is really cool. So what exactly am I saying? So we can add those two things together and say sum from minus infinity to n, sum from I equals to I equals n of a to the I equals a to the n plus 1 divided by a minus 1. And what I've done is I've added 1 over a plus 1 to this. So this minus 1 over a plus 1 went away. I think I've explained this pretty well. So yeah, I thought it was interesting. Just decided to share this. 12 minutes, fuck me.